Okay. I'm recording now. Let me share my screen as well. Can everyone see that fine? Okay. Cool. So, welcome back to Lecture 7. The original recording of this lecture was had the wrong uh, resolution, and so it only captured the upper left-hand corner of my screen. So we'll be doing this lecture again. The goal of today's lecture is to talk about matrices and linear systems. So we've talked previously a lot about matrices as linear transformations, but matrices, first of all, can be used to represent other things and also are kind of interesting mathematical objects in their own right. So we'll start with that. So for a little review, a matrix is a 2D array of numbers. We write A with this backwards E symbol in M raised to the n cross M to mean that A is a matrix with n rows and m columns. We will occasionally use A sub I to refer to the ith row of A, and we will very commonly use Aij to refer to the ijth entry of A. We've already discussed how you can use matrices to write down linear transformations. And in particular, if you have a matrix with n rows and m columns, then it will be a linear transformation that takes in vectors with in Rm and outputs vectors in Rn. The linear transformation is just any map between two Euclidean spaces that distributes over linear combinations. And they're incredibly important in a number of fields, and they're one of the most important reasons why we care about matrices. But matrices themselves are interesting as well. So we already talked some about some operations you can do with matrices, particularly matrix multiplication. But you actually can also add matrices, and you can scale matrices by scalars. So if we have two linear transformations, we'll call them T and S. This is actually pretty standard to see them as written as T and S. I don't know why it's S, but T comes from transformation, and S is just kind of just there. Then there's a notion of addition that makes sense, which is that if we add the two, it's the same as adding, say like T plus S applied to X is the same as adding T of X and S of X. And scaling a linear transformation by alpha is the same as scaling T of X by alpha at the end. So from these definitions, you actually can essentially uniquely define what it means to add two matrices and what it means to scale a matrix. So in particular, adding two matrices, you just get back the matrix whose entries are the additions of the entries of the two matrices. Now, I use this notation here to just mean a matrix indexed by I and j whose entries look like this. So this here is the matrix. It would be like x11, x12, x21, x22, for instance, right? So it's indexed by I and j, and this is what the interior elements look like. So right, this is just entry-wise addition. This is entry-wise scaling. And you have this property here that multiplication on the right is kind of distributes over matrix addition. Are there any questions about what we've talked about so far? the question is, when should you use this kind of indexing notation? The answer is whenever you're feeling lazy. So if you ever want, or if you're ever talking about matrices and you don't particularly care what size they are, you just want to talk about like something to do with their elements. In kind of both of these cases, it's kind of fine to just kind of write this kind of lazy notation. Any other questions? Okay. Now, another important thing you can do with a matrix is called this transpose. And this is something that you can do with matrices that you essentially can't do with vectors. We talked about how you can view vectors as column vectors, which are matrices, and then you absolutely can take the transpose. But you only can really take the transpose of a vector by viewing it as a matrix. And so the transpose is kind of this very simple operation, but it's very important. In particular, the transpose does is it basically makes every row of your matrix into a column. Or if you're doing the like ij index notation, the ijth entry of A transpose should be equal to the jith entry of A. And also note that it swaps M and N. So if A is an M by N matrix, then A transpose is an N by M matrix. And so here's an example right here. You can see like this row 1, 2, 3 becomes this column 1, 2, 3. This row 4, 5, 6 becomes this column. And actually, it turns out that the transpose essentially it has this property, this inner product property, and that actually turns out to be the most important property that the transpose has. In fact, if I just told you this, you could actually figure this out, the formula. So it's actually kind of like the definitional property of the transpose, which is kind of cool. And when I learned about the transpose, this was not told to me, and I had to find out later. So important equation here. Yeah. So that's a little bit about matrices as like objects in their own right. If you want to continue studying matrices, then the kind of next thing we'll talk about that's really like matrix focused is going to be like the 4 fundamental spaces and then eigenvalues. And then after that, the kind of field of mathematics that focuses on studying matrices is this field called matrix analysis. So the question was asked here, why are the terms in the scalar product switched here? And I'm trying to think if that's a typo. Which the answer is that might be a typo. Let me think. Okay, the typo is actually that that this y should be on the left and should be transposed as a column vector. So there's a typo there, but on the homework there will not be a typo. Okay, but yes, you're correct. I wrote this wrong. But yeah, anyway, thank you for pointing that out. Okay, so now we're going to move on to talking about something that you all should have seen in your algebra classes, and that's systems of linear equations. So linear systems of equations, or systems of linear equations, either one works. Are systems of equations, meaning there's more than one equation, that look something like this, right? So you have some number times some variable, and that variable isn't squared, or there's no square roots. It's just like number times variable plus some other number times some other variable, and then equals some other number, right? So these very simple equations, and very likely you've actually been asked to solve these in your algebra classes. In fact, I would say if you were not asked to solve something like this in your algebra class, then someone made a mistake. At least where I live, this is a state standard. And the goal, of these equations is basically to solve for the value of x and y. So these actually come up a lot. They might not look like this, but they come up a lot. If you've ever needed to intersect two lines, or actually intersect a line and a plane, or done, for instance, like ray tracing or collision detection, these all, at least implicitly, can use linear systems. In algebra class, you probably learned two different ways of solving these problems. You probably learned substitution and elimination. When solving linear systems, you can use by hand, you can use either, but when it comes to computers, you really do want to use elimination, and we'll talk about that in the next lecture. So let's try and solve this system. The first thing we have to talk about is what can we do to solve it? Well, if I have any equation, there are a couple things that I can do that are okay. One of them is that I can multiply either side by a non-zero number. Now, the reason it has to be a non-zero number is that I don't actually want to change what the answer will be. And if I multiply both sides by 0, I will have essentially erased both sides. I no longer have any information about what the equation should be. So if I have the equation x equals 2, and I multiply both sides by 0, now all I know is that 0 equals 0, which is trivially true. So you can't, but if I multiply both sides by 2, for instance, now I have 2x equals 4, I could still divide by 2 to find x, right? So that's why we want non-zero numbers. And I also can add things that are equal to both sides. So right, like if I have p equals q and I have that alpha equals beta, I can add alpha on one side and add beta on the other side, and this will not change the solutions to this problem. So this is basically, these are like the two things we're going to do when we're doing elimination. There's another thing you can do, which is like swap the order that you've written down the equations, but that's kind of trivially true. These two operations are kind of the more slightly non-trivial operations. And if you combine these two facts, what you can do is, if you know that two things are equal, you can always add a scalar multiple of one equation to the other. And this is like the most important thing we'll do. Yes, I also like my things. Anyway, so let's go back to our system of equations that we had here. What we want to do is we want to eliminate this x, this 5x. So how do we do that? Well, if we multiply our first equation, this one here, by 2.5, then this entry here will be 5x. And if we then subtracted that from this, we will get rid of this 5x, right? So that's exactly what we'll do. We'll multiply this by 2.5, the left-hand side. Then to balance it out, we have to subtract this from both sides, and then we can use the fact that 2x plus 3y equals 7 to get this this reduction. And so we end up basically just subtracting this whole equation from this whole equation. Sorry, this whole equation gets this whole equation subtracted from it. The x's cancel out. The y's, you're left with a negative 1.5, and then you're left with a negative 7.5 here. Now you can solve for y pretty easily. You get that y is 5, and then, okay, fine. You can substitute in now and figure out that x is equal to negative 4. Right, and so this is how you would use elimination and then a little bit of substitution to solve a linear system. Are there any questions about how we solve this system? Yeah, and also feel free to interrupt me if you want. You don't have to wait until I ask more questions. All right, moving on. Now, if you look at this matrix and you kind of squint your eyes and then unsquint your eyes and then turn your head, it should become pretty obvious that we basically have like two different blocks of information. We have this 2x2 block and this 2x1 block. And we've gotten pretty good at writing down blocks of numbers as matrices. And it turns out that you can actually do this. You can rewrite the whole equation as a matrix equation, right? Because if I matrix multiply this 2x2 on the left times this, the x goes to the 2, the y goes to the 3, we get 2 plus 3 equals 7. Then the x goes to the 5, the y goes to the 6, you get 5x plus 6y equals 10, right? And so we have this matrix equation. And all our method of elimination is doing is adding scalar multiples of rows to other rows, right? And so if we wanted to eliminate this 5 here, we just scale this first row by negative 2.5 and then add it to the second row. And we just have to make sure that we do the exact same operation to the right-hand side as well, and then we can solve the equation using elimination. And this is exactly what we do. We can store the entire linear system as just one matrix that we call an augmented matrix. And we put these little lines just to separate the left block from the right block. There's a question in the chat. The question is, do linear systems happen to have been the base for why matrix multiplication seems so arbitrary? No, the definition of matrix multiplication comes not from linear systems, but from linear transformations. But also, yes, because linear transformations and linear systems are also related. So yes, kind of, but it's better to think about matrix multiplication not being defined by systems, but being defined by linear transformations. Every single property of a matrix can be obtained by studying its linear transformation, and every single property of linear transformations can be figured out from studying the matrix. So it's better to think about that equivalence. So yeah, anyway, back to the solving the equation. You can solve the linear system then basically by just adding scalar multiples of rows, some rows to other rows, in order to basically make as many zeros as possible. In particular, we want to keep doing this until the left-hand block is diagonal, or as diagonal as possible. And this process is called Gaussian elimination. It's not the best way of solving a linear system in the world, but it is certainly not the worst. It's a very good way also of doing this by hand. Many of the better methods would be essentially impossible to do by hand, but this is a pretty good way of doing stuff by hand. In fact, the guy this is named after, Gauss, once used this to solve a 13 by 13 system of linear equations by hand, which is quite difficult for a human. Very easy for a computer, though. Now, another way that we could have solved this linear system, which I'll now basically forever write AX equals B, is to try and find some matrix or something, A inverse we'll call it, which satisfies this property that A inverse times A is equal to the identity matrix. If such a matrix exists, we call it the inverse of A, but not every matrix has an inverse. So non-square matrices, so matrices where the number of rows and columns are not equal, do not have inverses. If the number of rows equals the number of columns, we call the matrix square. When a matrix is invertible, though, we can solve the system easily just by multiplying by the inverse on both sides. And then we just get through this, kind of string of logic here that x is equal to A inverse times B. And it turns out you actually can compute the inverse of a matrix using Gaussian elimination on this augmented matrix here. There's a question in chat. It says, you say we call A to the name of 1 the inverse of A instead of saying that it is the inverse of A. Why is that? Because the reason I say that is because we have not said that the inverse is unique. Perhaps there's more than one inverse. And so, I don't know, saying that we call it the inverse versus saying that it is the inverse seems like a weaker statement to me. We're not claiming uniqueness. We're not claiming, basically anything about it except that it has this property. It turns out that if an inverse exists, there is only one. And so you could call it the inverse of, you could say that it is the inverse of A. But I prefer to say we call it the inverse of A. Until you've proven something like that. Now, on the first recording of this, I did not point out one of the implications of what I've just said, but I'm going to point it out now. For linear systems, there are 3 possibilities. The system can either have no solutions, meaning that the system is not solvable. It could have one solution, or it could have infinitely many solutions. Think about the case where A is invertible. If A is invertible, then I can solve literally any system. Given any B here, I can solve this system just by multiplying by A inverse, right? So if A is invertible, then every possible system of equations that I can make using A must be solvable. It turns out the reverse is true as well. If you can say that every possible system is solvable, then A also must be invertible. And this is exactly what this augmented matrix is doing. You're basically, by solving this augmented matrix, in a sense, you're actually solving every possible system of equations that you could write down with A as the left-hand side. And so in particular, it turns out that A is invertible if and only if every single possible linear system you can write down with A on the left-hand side is solvable. Are there any questions about the material presented today? I know it's a bit of a short thing. It was longer when we originally presented it, but there are fewer questions because I was presenting it for the second time. The question was asked, do you consider a system solvable if it has infinitely many solutions? The answer is yes. However, I claim that if any system has infinitely many solutions and your matrix is square, then it's impossible for every system to be solvable. Which that might be a lot, but basically like, if AX equals B for some B has infinitely many solutions, then there's going to be some other B where it doesn't have a solution. Um, yes, you can solve linear systems when the matrix does not have an inverse, sometimes. In particular, you can solve, um, for instance, the matrix the matrix where all the entries are zero. There is a solution for the system 0 times x equals 0, for instance. In particular, every vector is a solution. So there are solvable systems when your matrix isn't invertible. However, most um, most ways of solving linear systems assume that your matrix is invertible, basically. Um, some don't, and particularly the better ones don't, but many do. Okay, I am going to turn off the recording and then take any other questions.